In this introduction to line graphs, we're going to just do real quickly a simple word problem. We're just going to graph it. And this is the way the problem is going to go. You release a helium balloon well, how about while standing on a 10-foot platform? And let's suppose that the balloon goes up 5 feet every second. So the balloon ascends 5 feet every second. All right, now later we'll learn how to write these equations for ourselves, but right now we are going to be given the equation. We're just going to graph it and talk about what's involved in graphing real-life problems. So I have to give you the equation. Well, the equation that represents the height of the balloon is h equals 10 plus 5t, where h is in feet and after t seconds. So h is the height of the balloon in feet. In fact, we can say that h is the height in feet after 10 seconds. All right? So my equation is h equals 10 plus 5t, and I'm going to graph this. Well, when you graph a real-life equation, you have to think about whether or not it makes sense to have negative variables. That's one of the things you have to think about. And it doesn't make any sense to have any negative time. Time isn't negative. It also doesn't make any sense in this particular case to have a negative height. So I'm only going to be in the first quadrant. So I'm going to graph my equation only in the first quadrant. It doesn't make any sense to show the other quadrants. Now, I'm going to pick some different times, and I'm going to see what h is at those different times. So t is like my x here. So I'm going to label the x-axis t. You always want to label your x and y-axis with the variables in your equation. And you always want to include the units. So t is in seconds. And then this axis is going to be h. It's like the y. And it's going to be in feet. All right, so I've labeled my axis with the units. Now I'm going to pick some different t's. Well, let's start with t equals 0, because that does make sense in this problem. At the beginning, t is 0. So when t is 0, and I'll put 0 into t here, then I get h equals 10. All right, well, what about when t is 5? All right, well, when t is 5, 5 times 5 is 25, plus 10 is 35. All right, what about when, let's say t is 10? Well, when I put 10 in for t, then I have 5 times 10 is 50, plus 10 is 60. So here are 3 points that make sense for this problem, all right? So on the t-axis, I could count by 1s or 2s or 5s. Really don't want to count by anything higher than 5s. Probably I'd really rather count by 1s or 2s. So I'm going to count by 2s. 2, 4, 6, 8, 10. But on my h-axis, it doesn't make any sense to count by 1s or 2s, because look at the numbers I have for h. What makes more sense is to count by 10s. These are some decisions you have to make when you're graphing a real-life problem. And notice that I don't have to count by the same numbers on both axes. They can be different. All right? Okay, so I've tried to space these evenly. You would do yours on graph paper. Well, let's plot these points. When t is 0, h is 10. All right? when t is 5, well, I haven't marked a 5, but I know 5 is halfway between 4 and 6. Then t is 35. So here's where 35 is. Here's where 5 is. So there's a point on my graph. All right? And then when t is 10, h is 60. All right? Well, let's come over here. And there's t is 10 and h is 60. So I can connect my points. When I connect my points, I see that it is a line. All right? And you want your graph to take up your picture. You don't want a little bitty graph way over here, up here somewhere on a scale like this. If your graph ends up looking like this, you need to change one of your scales. All right? And you also don't want to be drawing the line past this point because, remember, negative values for this problem don't make any sense. So when you graph a real-life equation, remember to think about the practical parts of that problem.